Yeah, so welcome everyone to High Performance Computing. After some challenges here in the room, we finally can get started. It's also nice to see at 8 o'clock a quite full room. That's quite unusual. But yeah, welcome again at the University of Iceland. Who of you have used high performance computing before or have heard about it? Okay, not so many. Don't worry, we will start basically with really simple details. Starting from scratch, so to speak, and will evolve over time really to advanced topics and then really how we can use it. I should say also this year we have a sort of special high performance computing course. You see my fellow teacher Reza there, maybe stand up that everybody sees you again. He will take care more of the second half of the course, which is then really to a specific field in physics called computational fluid dynamics. Doesn't mean anything to you. Don't worry, we will see how that materializes when we come to the end, basically, of the first part. So from the topics perspective, and there are lots of logos and they have all a meaning, and I tell you why, because we get lots of money from the European Commission, and we sort of really have this course tuned for several topics in these research projects as well. That's why we come to these also logos, not only today, but also in the beginning of the courses. So from today, it's really a lecture which is a prologue. So we have lots of questions, answers to solve, and wait, I will have probably many answers already prepared since we're teaching already. That's 10 years now, this particular course. From the outline of the course, we will start really with fundamentals in high performance computing, meaning what really is high performance, why we say this. This brings us quickly to using parallel programming. So not just using one GPU, we're using 1,000 GPUs in parallel. So these are things which we basically materialize in the first parts. And then we come to something called the message passing interface. It's basically a programming model for performing parallel programming. And we will talk about how that works in, let's say, massively parallel systems. And then we have something called shared memory programming with basically OpenMP, leveraging then also a lot of memory. Memory is very fast in computers, so it's also very good to leverage those. Then from the topics, several people of you have probably heard from GPUs. Who heard yours from graphical processing units? GPUs, I guess it's pretty known from the gaming industry. But here we're talking about how we use it for science. So in this sense, it's not really GPU, it's more or less GPU, general processing GPUs. And we see how that works, especially today there's NVIDIA, but also AMD GPUs. And some of you have heard probably deep learning. Who has learned about deep learning or heard about deep learning? Deep fakes? The most people probably, right? So it's a very hot topic. And deep learning is really fueled by high performance computing. You cannot do deep learning at scale and a really proper model if you don't use high performance computing. And we will see how that materializes when we have here a couple of lectures actually, and also some parts of your assignment will be related to it. These are basically very fundamentals, and normally we dive off. You have maybe seen the YouTube channel. We dive off then in different areas of science and engineering because HPC is quite used broadly. But here in this particular course this time, also because Reza will be a co-teacher here, and he is a senior PhD student, almost finishing basically, he will dive with you then more into the field of computational fluid dynamics. So this is a field driven by physics, and we will come to each of the topics one by one. And different methods will be shown how you actually perform CFD, but we start very practical with a OpenFoam software, seeing how basically avalanches, for instance, in Iceland can be crafted and modeled with OpenFoam and then solved with this CFD, which you will learn about. And CFD was really driven by fundamental physics, physical laws, numerical methods, and so on. But these days, we see also a lot of AI, artificial intelligence, deep learning coming. So in this sense, we will also show you a little bit how deep sequence modeling is nothing else than time series data, basically, to analyze how that works. And then diving into different fields of CFD at the end. We finish with a very hot topic where we do lots of research in, and which is actually coming to some of the problems in Europe, green energy. It's not so much a problem for Iceland, as many of you know, but a huge problem for everyone in Central Europe, including Germany, for instance. We had to shut down our HPC systems. We had an energy crisis when the Ukraine war started. And of course, there's lots of research around green energy, also for the, let's say, general public to have more green energy. So you see, we did quite a wild mix of practical topics and theoretical topics. And this has a reason, because we developed this course over years. And of course, you don't want to have the assignments all at the end, right? So that's why we have every now and then sneaked some more practical lectures in to do the assignments early. What is not here in the agenda is basically some practical slides that I will always present, or Reza will present, or we have even other PhD students. I have a team around 15 people here. They will provide you with a practical lecture 2.1, for instance, or 5.1, giving you demonstrations of basically more parts of this, let's say, more or less bigger fields. Alone MPI, for instance, you can take around 3-4 days to really master it, right? So usually in my center in Juelich in Germany, we do this for 5 days in a row, from morning till evening, and then you know what MPI is. We don't have time here in the university for all of that, but at least you get some concrete topics at hand. So thinking about the first part then, and when you have questions, please raise your hand, but maybe the first part is really about answering, hopefully, many of your questions about the course organization, motivation, and so on. So we have this large field, high performance computing. We say it's a Formula 1 of computing. We have always the highest, biggest machines. And maybe some probably have heard we'll get an exascale machine. Do you know what an exascale machine is? No, okay, that will be also coming very quickly. We get in Germany the first exascale system, high performance computing in Europe. And this is basically meaning nobody has done that before in Europe. So it's basically meaning it's the Formula 1 of computing. It's not traditional computing. And you will learn why we do this. It's also not something where you do a little bit of MATLAB or scikit-learn or whatever, or small application packages. Usually they're motivated by very specific domain sciences, right? That's why you have here these kind of stretches in. They really drive high HPC. We call this co-design. So it's not that we build a machine, please use it. Usually we get the requirements from domain-specific sciences and engineering, problems, applications, weather forecast, for instance, is one of them, climate on the long end, and destination Earth, a digital twin, another. And by doing so, we have this course crafted so that you can use this really in different domains. The CFD special that we have now, that we introduced last year, is a little bit special, but still many concepts you will see inside these, you can take also to other domains, like for instance, time series analysis with deep sequence models. You basically can get the idea and put it to other time series data sets. Hence, the course is quite a nice combination, but of course, just an introduction to high performance computing. There's much, much more to this topic. These days, we have even a master of HPC in Luxembourg that you can do, which is basically then meaning you have lots of more fields to study if you're interested. So for the motivation, it's really about a field called parallel. Hello, welcome, just sit down. We have really parallel computing, distributed computing, which is basically one of the core ingredients why we come to something like high performance. But it's also about driving it with different, let's say, challenges. And here, when you see normal scientific computing, where you have, let's say, MATLAB. I mean, some of you have probably heard MATLAB, scikit-learn before, right? There you have one computer, but there's an end to memory, right? Let's say you want to analyze 500 terabytes, then your memory in the computer can't do that, right? So there are limits in this traditional scientific computing. And the same is true when you do some cutting edge deep learning today. You could maybe use a workstation client with one GPU for hours, maybe days, while in high performance computing, you can do it in an hour. Of course, by employing then 500 or 200 GPUs in parallel. And that's what we learn and what we, so to speak, see a little bit as advanced scientific computing. This is a very relevant field, but the serial limits is something we will address in that course and solve with then parallel computing using basically these large high performance computers or supercomputers. So what you really should then learn coming out of this is the latest developments. When I said, okay, exascale system will come in Europe, actually there will be two. Jules Verne is also in France coming up. You will learn what these buzzwords mean: exascale, petascale, parallel computing, MPI, OpenMP. There will be lots of abbreviations you don't know anything about now, and that's all right. But domain decomposition will be part of it, how you basically crunch down a big problem into smaller pieces. And at the end, of course, you will have also really good foundations in CFD. But yet again, I think you should also see that as the idea of how you apply HPC to domain-specific sciences and take something out in the sense that you can apply it also to, health care and wherever. And with this, we have hopefully a good course again. As I said, it's basically built on student feedback since 10 years now. So we have got also in YouTube, very good feedback on this. And everything will be recorded, all the slides, also to get a question forehand. I guess it's always asked, it will be all recorded, all the practical lectures, all slides will be available. So you don't have a need here to really make too much notes maybe. Just a short background, because we will also use some computing resources in this particular center. That's where I come from, basically 20 years working in the German supercomputing center Juelich, that's close to Aachen or Köln, in the middle of nowhere really, because we used to be a nuclear research facility, but nowadays we really have a science campus with 4,000 people roughly, and the supercomputing center is one of them. And we will use some of the resources from these HPC machines, which are situated and located there, but that's not a problem because we can remotely access them easily via the internet. And this is something what we also will learn in the course. So hence, the first parts will be something like the secure shell protocol. You have heard from SSH before, maybe secure shell. Okay, good. And Unix as well. Fantastic, good. It's still good to see that some people learn this because more and more I'm exposed sometimes to just Java and apps development and so on, students that never heard from Unix. However, those that don't, we provide a practical lecture 0.1 that will be actually tomorrow, where I show you a couple of details on how you work with Unix, how you basically use the SSH protocol before we get really started. Yeah, so I have the right to talk to you about HPC. As I said, I'm 20 years in the field of HPC. I love it. It's, of course, one of my passions, and have done many positions at the Juelich Supercomputing Center. And I'm a professor since 10 years here at the University of Iceland. That's majorly a kind of research group collaboration with around 15 to 20 students going back and forth with Germany and Iceland. One of the reasons is that the Juelich Supercomputing Center is just a national lab. Right, so we are not really tenured there. So we always team up with different professors in different universities. We have around 10 or 12 professors at Bochum, at Aachen, at Leuven, and I'm in Iceland. So said this, of course, there are lots of EU projects, research projects. And why? Because we are having, of course, our applications mostly derived from that. We do a lot of research, a lot of engineering problems are solved. And with this, we get also as scientists lots of funding for providing this as an infrastructure. And there's one key, which we will learn also more and more in the course here, that is the Euro-HPC joint undertaking, which provides us for free resources. So when you go out of this course, you cannot say, well, I learned about HPC and cannot apply it because I don't have resources. Everybody in Europe has access to HPC for free. And I will show you how that works in the Euro-HPC joint undertaking. There are several systems online. The only trouble is you have to do a small proposal to get computational time. But this will be also part of our, let's say, endeavor, so that you can go out of this course here and say, I would apply it in my company, in my startup, and I can also get the computational resources and I know where. Hence, the Euro-HPC, still relatively young, will be a major part through all the different lectures, right? Because this will be relevant for software application packages. It will be relevant who is having, which architecture of GPUs. For instance, Lumi in Finland, the system where Iceland is also part of, has AMD GPUs, not NVIDIA GPUs, which the majority have. So there are different architectural constraints and challenges we also discussed in the course. From the university course perspective, this is built basically on lots of experience over the years, as I was saying. And we blend in several times also elements of machine learning, AI, statistical data mining, for a reason that you have also, let's say, not only physics problems to be solved with computing, but also essentially some AI topics, which are very popular these days. And you could say that basically also, AI is a major driver of our HPC field today. And I think before I introduce here Reza, I think it's good that the audience also hears you a little bit. So wait a second.
Hello, everyone. Thank you, Moise, for this opportunity. I'm Reza. Currently, I'm a PhD student at the University of Iceland, and I'm working with the Moise Research Group. My focus is mostly on the CFD, Computational Fluid Dynamics, and we did some experimental work on the fluid dynamics, and also currently we are using the deep learning and high-performance computing for some unsolved problem in the turbulent flow. In this course, I will take over for the second part of the lectures, and we will talk about the computational fluid dynamic and how the HPC is required in this field. The computational fluid dynamic mostly solving some problem which is required to solve by the numerical methods. When we are talking about the computation and numerical method, usually we need the computing. Most of the problem in the CFD, when they are in the actual size, we cannot solve them with the regular systems, which, you know, like the PC or the laptop. For example, recently we were working about the solution for the problem in the DNS, direct numerical solution. It's required 15 million CPU, so we can recognize how much the computing is required in the CFD. And of course, in this introduction, I will talk about the second part of the lecture from 8 to 15, what we are talking, what about the CFD, and how we will talk about the deep learning and high performance computing, and also we will have some introduction about the application of the CFD in the energy. And in this slide, you can see a short introduction about our activity in the recent year in the Moise Research Group. And thank you, Moise. And I leave it for Moise.
All right. Yeah, thank you very much, Reza. So I should also add he's a very good senior PhD student. So that's why he has also the opportunity to teach, and hopefully we can also grab into the academic life. This for PhD is always a very interesting time, stopping the PhD and maybe going to industry. And of course, we academics have also a little bit the hope that we get youngsters again as professors. So one of the ideas is also here with this course that he learns how to teach. So I hope we have also a good, basically topic here for you, and this will be all interesting. Some of you maybe come from other domains, and I know this might be then a little bit like shaking up CFD and so on, but we have also some ideas that for final projects, we come to this in a minute, you can also maybe dive off into other domains, right? So let's just think about that CFD will be one of the main parts in the second half by Reza. Good. Generally about the University of Iceland, you are all here. So I think in one way or another, you probably have looked at this already. So I go here a little bit faster now. And again, describing a little bit why you see so much logos, why that is all connected to HPC. So you see essentially a structure of the Juelich Supercomputing Center combined with the University of Iceland, a research group, as we said, we built since 10 years. And many of the people you see, including Reza, is funded by European projects, majorly in different areas. Reza is part of the National Competence Center under the EuroCC umbrella. We have a RACE, Center of Excellence in Engineering, where we have AI on physics problems and other European projects. And they all give you a couple of millions of euros for people. Hence, we have around 15 people or 16 people that do lots of research, not only in technology on HPC, also, as you see with Reza, majorly working on CFD application research. Hence, these logos are important because also we are funded by them in parts. Hence, I have to raise this here a little bit, but they also show you a little bit the interesting way how HPC is developed over the years. As I said earlier, it's not just a laptop that the manufacturers build together and then please take it. We usually have this different domain-specific simulation and data labs applications in very different areas of science, neurosciences. You have here brain sciences as well. And then, of course, the traditional physics, CERN, and weather, climate, not forgetting this. And they're all sort of basically shaping the design requirements of this HPC machine. And when we come to this, we will see that several of these applications have really completely different requirements. Weather forecast is really depending on the direct neighborhood of your situation, right? The weather, which is here in the next GPS coordinate, is exactly also relevant. So they have to communicate a lot with each other. You have other problems in science where you have lots of data, but you can analyze them separately and at the end merge some result. So the neighborhood has no basically big impact at all. It's just the throughput and the high performance throughput we are looking in. Hence, at different requirements from all of these different applications and data, we should also include data significantly here, which then basically shape the design of these large facilities. Hence, you will see also when we come during the whole course, they are very different HPC machines, right? They're basically tuned for different requirements, AI machines, physics machines, and they will all look a little bit different. Some even have specific industry relations and industry part of it, like containers. Not sure if you heard this already, Singularity or something like this, containers, Docker, containers, yeah. So this is entering the HPC domain as well. So this is something which is traditionally more in the industry domain. The scientists are just starting with this. Yeah, and then of course we want to get it to the general public. You will be invited to the eHPC workshops we do every 2 months. And this is also driven by our European Digital Innovation Hub of Iceland. So this is something where we always have to see, we burn a lot of taxpayers' money. The exascale machine we get in Germany is quite expensive. So we have one mandate, and you see me always here doing photos here and there and so on. And when you see on my social media channels, we have to also expose a lot what we do to the general public because we get lots of taxpayers' money. Hence, we are also doing lots of outreach via these different projects. But one key aspiration is really this heart. So always think about HPC has a really tight connection in a way to application sciences. And we will learn many of them as examples throughout. Again, also for you as a sort of invite, look at the webpage from ehpc.is, our National Competence Center in Iceland, which is tightly bound together with Germany and a couple of other, let's say, European national competence centers. In general, there are around 36, if I'm right, in all the different membership countries. So no matter where you're from, I think we have always some Erasmus students here. There's probably also national competence for HPC and AI in your country. This also brings me to the opportunity to see the larger science area. So I don't know if some of you have heard the European Open Science Cloud by chance. It's entering science and engineering in a way that, you know, you preserve data sets, you make data sets fair, basically findable, accessible, interoperable, and reusable. That's a big statement. We will learn this a little bit here in this lecture, but there's another cloud course this fall, which goes into this parallel computing area more intensively. So here we really focus on HPC, the European joint undertaking, as I said, for you, for resource provisioning, for resource access. And here and there, we dive in several research projects, and you will see some of my PhDs or postdocs will talk then about these projects with some interesting parts to different lectures. But here again, please have a look at the ehpc.is website. In Canvas, it is already linked as a one resource in the module, if you have seen. And I hope that everybody has access to Canvas. Is there someone who has not access to Canvas yet? Sometimes international students? No? Okay, cool. Very nice. So this has been much better fixed than in the last years. Just quickly a little bit, and we go into this much more in depth in the next basically couple of lectures. How you can differentiate the topics of high performance computing versus high throughput computing and the things we do more in cloud computing is often that the HPC machines are really tightly integrated systems, right? Multi-million of costs. And the point is also that these are really expensive machines because they have certain interconnects. They connect the different parts and ingredients, let it be GPUs, CPUs, very tightly together. For instance, with InfiniBand, that makes it very costly. But for this is something where you basically can see that weather forecast and these aspects, which really have a tightly integrated need of the neighborhood, they're very well supported here. While when you have a high throughput computing machine, you basically have no good interconnects between the different ones or Ethernet, so something, let's say, standard, then it will not work very well. And these are the interesting parts Also, we do some quizzes in the course. That's why you see here the yellow parts. This is something where when you have the whole course, please take this by heart a little bit. These are the most significant parts that should be hopefully in one way or another end up in your brain. And again, the invitation to look at the fall course, if you're more interested into cloud computing, this will be coming up this year as well. There will be, again, many of the different, let's say, abbreviations we will cover. And here's a good opportunity to understand what really a supercomputer is. So you can consider usually a very large room with lots of racks, a second floor. And you see here that the installation of a new HPC machine on the same location actually takes days, sometimes weeks, even up to months, right, to get it really operational, to test it and so on. And it has lots of interesting things like a gas hole, which might be, for fire problems. So you don't want to have water, of course, coming when there's a fire. So there's lots of infrastructure just around the HPC system. And then we will learn a bit, how we come from one floating point operation per second, then to the exaflop, which I said is now the system being installed in Juelich and soon also in France, in Gency or CA. And all of these details is just a more appetizer here. That's why it's a prologue. We will go into more detail. But think about, of course, that this is a very high, let's say, attractive topic these days. It really grown from the time where I started from 2004 with a power IBM architecture, then in 2 different regions with a really scalable path, if you want, using lots of GPUs. While you have also the other part, really general purpose clusters where you have high single thread performance, right? So it means the CPUs are very powerful, while here they can be weak because we're using GPUs. Here, basically, we need really tough CPUs, number crunchers to solve physical problems. And this is a kind of element which we also will discuss in the course. We call that modular supercomputing, which then means that one supercomputer essentially in itself is broken into different modules for different purposes. And this was part of the deep project we researched and is nowadays also installed in Juelich via the Juelich system, via the different, let's say, systems in HPC. And also the exascale system in Germany will be developed based on the modular system. You see that here a little bit, again, the ideas of modules. And this is actually, again, co-designed by the needs of different communities in HPC. As I said, from neuroscience, completely different than space weather or earth science. And we created then this different modules for the supercomputer, mostly, again, the extreme scale that you have seen on the one side, then the cluster module on the other. But also nowadays, we see significant storage and big data in real life, so terabytes and so on, and even more petabytes coming. And then something we call the data analytics module, which is more things like Spark, more, let's say, data analytics in terms of throughput of data analysis. And this is just, let's say, again, an outlook. There's no need to understand all of that directly. It's just more what the kind of course is covering. We will use some of the deep systems here in the course. So it's basically a HPC system. You get hands-on experience. You do practical problems. We do also practical lectures to show you how. So don't worry if you don't know about SSH scheduling and all of that. This is all coming up one by one in the different lectures. So in terms of the course motivation and organization, we should switch maybe a little bit how we run the course. And this is mostly done via Canvas, as everybody has now access to Canvas. I think that's already good. I hope you all get the reminder of the lecture also that was working. Okay, yeah, everybody got the information. So we will run this basically as we have seen now. There will be announcement that the lecture is. We will do definitively the modules with all the informations you have already seen. Of course, the recording is not linked yet. We will upload that to YouTube and then link it from there. The slides will be uploaded there. The assignments will be driven there. So basically, you will see that parts of it will be coming with some assignments around 3. We will discuss this in a minute. So everything should be around there. Of course, when you have problems or so, we have also office hours, right? I should say I'm in Groska with Reza on the other side of the campus. It's close to Decode Genetics. But please contact us or my assistant, Katrin, to really book some office hours. We will see that this course, particularly being Monday morning, will be a little bit, let's say, more remote done, I think, because as I said in the email already or in the message, It's particularly hard to come here at 8 o'clock, at least for those that have kids, or basically also because of the weather. So for the first 2 months, we probably have the Monday lecture online. Coming to the overall course organization is probably one of your next questions, what we will do, how it is organized. So we have this basically outline of the course with all the slides you have seen. This will be the major driver of content, but then we will have also 3 assignments, and they're very close related to our practical lectures that we will do. So some of you can also, maybe if you want, go already to the YouTube channel, go to 2023, because it will be very similar what we have done there. Right, you will see several practical lectures. Of course, we will redo them here in the course, but to get an appetite, if this course is really something for you, I recommend also to maybe take some time, go to the 2023 YouTube part, and then you see the lectures. This will be 40% of the grade, but again, there will be step-by-step, ways how you solve the assignments. It will be not that you basically have to learn from scratch all about HPC. We will take you there, especially because these HPC machines are not like a normal laptop. Then based on the feedback we got from students, we do also quizzes and the final project instead of an exam now. In traditional times, we did an exam. Now students want to have usually more a final project, as our surveys say. So we offer that here in the course. This is something what will come up a little bit later. So we have to establish the ground first, and we will give out some projects. But if you have, let's say, an interesting research project from one of your research activities, some of you are PhD students already, then maybe we are also very open-minded to integrate it as HPC inside that, right? So that you basically can apply it to your specific domain science field. So, however, this would be the structure. The quizzes will be 10% of the grade, where we do every now and then a small, test quiz, which is also done via Canvas remotely, where you basically then have to see that you learn hopefully a lot about this yellow blocks, right? So again, the yellow blocks are very important. I always, and Reza also summarize the most important aspects in this yellow blocks. And if you have done the yellow blocks very well, the quizzes will be no problem at all. Yeah, so much for the course organization and activities. Grading will be later also done via Canvas. There's one additional tool called Add, but maybe some of you have already heard from it. It's basically for discussion in the course. So we will do an Add part of this course as well for entering the discussion. And also here and there, you see once per week Q&A session we will see, maybe every 2 weeks, depending on where we go. There will be also several occasions where I'm on a conference. I'm a very active researcher, as I said, so sometimes there's just no course and you have self-study time for your assignment, but it will be all announced over the time. And yeah, basically this is just examples. And at the YouTube channel, I already said it will be uploaded majorly because, several parts of it are really funded also from EU projects, and we are mandated to put that out into the field so that many others can also benefit. And we get actually substantial good feedback and, good quotes also from others that actually looking this outside the University of Iceland or Germany. And again, there will be all the materials online. But this course has been developed over a couple of years, so there are many lectures that you will see in our outline that have been already taught a couple of years ago. So here and there, it might be interesting to sneak also through these different years. Yeah, social media is another part. We are very active in this. You will notice this when we do our HPC workshop here. You maybe even participate in 2, in February and in April. There always be monthly, every second month, where we have cheese and wine, but also interesting discussions around HPC, always with high-class invited speakers that tell you some really from the practical details from companies, from universities, and so on. Literature is basically very dynamic via the different references here. There's one book that might be interesting, but I would say these days, as everything is accessible via the internet, don't worry about the book. I will probably mostly always give you all the references in the lecture bibliography afterwards, and it will be open, right? So I would say in these days, don't really buy this book, but if you have access to this book, especially in the beginning of the course, it might be interesting to look at it. But in HPC, it's so fast. Books, when we write them and publish them, they're basically already outdated. So here you see some feedback from the course. And of course, we also would love to have your feedback. this also concludes the first part. I just want to show you one interesting video, maybe as a summary of the first part, and then we go lecture by lecture in the second part, what we really could, see under the big bold headers of the lecture.